This is question number 2 from the linear algebra exam from 2015. So you can see part A, we have two lines in three-dimensional space. We want to determine whether or not these lines intersect, and then we want to find the shortest distance from the point 1, 1 minus 7 to the line L2 here. And then part B, we want to find a Cartesian equation of a plane given these 3 points lie in the plane. So for part A, we have these lines here, L1 and L2, divided by these vector equations. So if these lines meet, then the x, y, z values have got to be simultaneous at one point. So the x, y, and z has got to equal x, y, z. So therefore, 1 minus 4, 2, plus r times this vector should equal the vector equation for L2. Which means that the components on each side also have to be equal. So if we look at the components, the first component, we have the equation 1 minus r on the left, and on the right here you can see we've got 1 plus 0s, so that's just 1. So the first equation is 1 minus r equals 1, so obviously r is 0. For the second component, we have minus 4 plus 0 should equal 4 plus s. So we have minus 4 equals 4 plus s. And equation 2 gives us s is minus 8. So we have r is 0 and s is minus 8. Now the third equation is given by the third component. So we have 2 take away r equals 1 plus 2s. But if we put r is 0 and s equals minus 8 in here, you will see that we get a contradiction, which means that these lines do not meet in three-dimensional space. Now for the second part of the question, we want to find the shortest distance from the point 117 to this line, L2. So we suppose that x is perpendicular, x is a perpendicular point on the line, which has x is a perpendicular point on the line. And the line is 1 plus 4s, 1, 4 plus s, and 1 plus 2s. That's our line L2. So the vector ax is given by 0, 3 plus s, and 8 plus 2s, because ax is the vector x minus a. So we just do x minus a, and that gives us this vector here. So here's our a, and here is the coordinate position for x. So this is the vector x minus a, which is equal to ax. Now this vector is perpendicular to the line, so therefore this vector is perpendicular to the direction vector for the line, and the direction vector for the line is just 0, 1, 2, which you can see here. So this is called the direction vector for the line. So our vector ax dotted with the direction vector for the line should equal 0. That means that these two vectors are orthogonal. So we take the dot product, we get 19 plus 5s is 0, which gives us s is minus 19 over 5. So the vector ax then is found by substituting s is minus 19 over 5. So we substitute s is minus 19 over 5. Here is our vector ax, which is perpendicular to the line. And to find the length of this vector, we simply use the Euclidean norm. So we just take the square root and then we square each component and add them together. And you'll see that the answer is the square root of 4 over 5. And that concludes, oh no, that does not conclude that. Okay, so now we've got part B. Okay, so for part B, we've got a plane contains these 3 points, and we want to find a Cartesian equation of the plane. So these 3 points lie in the plane. So to find vectors in the plane, we know that, for example, AB, the vector AB, which is B minus A, is a vector in the plane, and AC, which would be C minus A, is another vector in the plane. So you'll see here we've got, so A is the vector AB. So AB is found by doing B minus A. So that gives us the vector 6 minus 1 minus 3. And B here is the vector AC. So AC is simply C minus A, which gives us 2 minus 3 minus 1. To find the cross product, we take the determinant of this matrix, So the I component is this times this, take away this times this, so that gives us minus 8i. The j, remember we negate, so we have minus 6, and then plus 6 is 0, and we negate, it doesn't matter really. So the j term is 0. And finally for the k, we have minus 18 plus 2. And minus 18 plus 2 gives us minus 16. So this is our normal vector to the plane. Now these coefficients here are the coefficients of the x, y and z in the plane. So therefore the equation of the plane is minus 8x plus no y minus 16z equals some constant which we'll label as p. Now to find the constant p, we just substitute one of either a, b and c back into this equation because these points, remember, lie on the line. So in this case, I think we substitute the point b. So x is 5, y is 2 and z is minus 1. We substitute those values into here and you'll see that we get p is minus 24. So a simple rearrangement of the equation gives us the equation of the plane is equal to 8x plus 16z equals 24. So that's the Cartesian equation of the plane containing the points A, B and C. And that concludes the solution for question number 2.